This is Physics 220, which is Physics 2, Classical Physics 2. All right, well, that's good. And we're in Chapter 21, Working Problems. We'll start with problem number 6. And we have dust. So we have two dust particles, and they exert, and they're charged, and they exert a force on each other of 3.2 times 10 to the minus 2 newtons. And so here there's dust particle 1, there's dust particle 2. It has some force. The force is a positive force, so it's an attracting force. The issue is, what will the force be if they're moved to 1/8 the length, the distance? So I've got some distance there, and I've got some new distance, d over 8. Alright, so that's the issue. We look at equation 21.1, and we find that force is equal to 1 over 4 pi epsilon naught q1 q2 divided by r squared, and we come to the conclusion that force is proportional to 1 over r squared. Okay, so that being the case, then the force at 1/8 the distance is going to have to equal the force naught that I began with, dividing by that 1/8 the distance squared. And so that's going to be 64, the original force, and 64 times the original force of 2.3 times 10 to the minus 2. Put that on our calculator, see what we get. 2.3 double E minus 2 times 64. And we only have two significant digits, so we're going to call it 2.0 newtons. And that would be the force that they would exert at each other at 1/8 the original distance. Okay, next problem is number 12. And we have 3 charges sitting in a line, which is always convenient. So we have a charge of 75 microcoulombs. I left the plus off because it was implied. Plus 48 microcoulombs and a minus 85 microcoulombs. And we're, they're equally spaced, 0.35 meters, 0.35 meters. Now, when we do the force is equal to 1 over 4 pi epsilon naught q1 q2 over r squared, when we do that, the r needs to be in meters. So keep that in mind. All right, well, what does the question want to know? The center one is blah, 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 blah. Calculate the net force on each charge due to the other two. All right, so we want to know the force on the 75 microcoulomb guy. All right, so we have 1 over 4 pi epsilon naught 75 times 48 microcoulombs divided by 0.35 meters squared. And we see that that's a repelling force, so I'm going to put a minus sign there. And I see that the other force is going to be attracting, so we'll put a plus sign there. 1 over 4 pi epsilon naught 75 microcoulombs 85 microcoulombs divided by 0.7 meters squared. And I run all those numbers through my calculator, and then I also say to myself, I am in the x direction here, so I'm going to put a I hat sitting there and an I hat sitting there, so I know that this force is in the x direction, and I'm going to end up with minus 172.2 newtons in the I direction. And then I'm going to say so that so it looks like the repelling force wins, and I'm going to be moving away. Anyway, I only have two significant digits, so I'd have to go and say, well, final answer is only going to be minus 150 newtons I hat, because it is a vector, the force is a vector quantity, so we'd have to have a direction thrown in. Okay, well, that's one down. Now we need the force on the 48 microcoulomb guy. And so we do the same thing. We're going to do it differently, of course, because we can't do it the same way every time. So force on a 48 microcoulomb guy is going to be K, 75 microcoulombs, 48 microcoulombs, 0.35 squared I hat, and these guys are going to be repelling, so that's going to be negative, and then we're going to go with K. Now K and 1 over 2 pi epsilon naught are the same thing, so perfectly okay to do. 48 microcoulombs, 85 microcoulombs. These guys are attracting each other, and that's why it's going to be positive 0.7 squared I hat. Okay, so I'm going to run those through my calculator. I'm going to remember that when I do that, K is equal to 8.988 times 10 to the 9th newtons meters squared per coulomb squared. Normally, if I'm not looking for a lot of significant digits, I'm just going to put in 9 times 10 to the 9th in my calculator. And I run those numbers into my calculator, and I come up with 563.5 newtons in the I hat direction, which again, I only have 2 significant digits, so I'm going to call it 560 newtons is going to be the force on the 48 microcoulomb guy. And then I'm not done yet. I still have to find the force on the minus 85 microcoulomb charge. Now these are going to be attractive forces. So I'm going to attract it, but it's going to be in the minus direction, is it not? You think about that. Yes, it's going to be in the minus direction. If I come back up here, this guy's being pulled towards him. He's being pulled towards him. So when I get done, I'm going to be negative. All right. So I'm going to have minus 1 over 4 pi epsilon naught. I like those guys better. 85 microcoulombs, 75 microcoulombs divided by 0.7 squared meters. Minus 1 over 4 pi epsilon naught, and 85 microcoulombs, 48 microcoulombs divided by, that's a capital C in case anybody's wondering, 0.35 meters squared. And I'm going to run those numbers through my calculator. Minus 416.3 newtons in the I hat direction. And again, I only have 2 significant digits in the problem, so I'd round that off to if I could put the right units down. 400 minus 420 newtons in, and of course the negative sign there really means I'm going that way and I'm in the x direction, right? So that's what that means. I'm coming back up to this guy and I'm reconsidering for a moment. Force on that guy is going to be in the positive direction, and that's going to be in the positive direction. Yeah, so both of those guys are positive, and that's when I put it in my calculator. I did it that way. Okay, so much for number 12. Number 20. Okay, we're doing number 20, and we have two small charged spheres hanging on cords of equal length L. And so I got some overhang, and I have L going that way, L going that way, and I have some spheres sitting here on the bottom. All right. And I've got Q1 on one side, and I got Q2 on the other side, and I've got some angle, theta 1 and theta 2. And this will take more than the average picture. All right, and then angles theta 1 and theta 2 are small with the vertical. Well, what does small with the vertical mean anyway? Well, small with the vertical means that probably means that I can equate theta is equal to sine theta as long as I'm in radians, right? So we'll probably do some trick like that later on. All right, so problem number A. If Q1 is equal to Q and Q2 is equal to 2Q, and the M's are all the same, the masses of the spheres are the same, determine the ratio of theta 1 to theta 2. Okay, so Q1 is equal to Q and Q2 is equal to 2Q. Okay, and the masses are the same. Okay, so we have all that down. All right, so let's see now. And we look at that and think, well, let's see. We got some force due to gravity, right? And we have some force due to the charges. So we got some force due to the charges, and the summation of those forces have to be 0. So that being the case, the force due to gravity had better be equal to the force due to the charges. All right. So what we're going to do is going to look at, I've got some, this is Q1, so I got some force going that way, which is the force due to the charge on 1. I have some mg, which is my gravity, and then I've got some tension, force due to tension in my rope. And then I got over here, I've got Q, I have theta 1. Theta 1 is my angle. So that's that picture there. Okay, so the look at the summation of the forces in the x direction. All right, so that's going to be the force of tension times the sine of theta 1 minus the force due to the charges. All right, so that implies that the force due to the charges, and then those forces have to equal 0 because these guys aren't moving. The force is equal to charges is the force of tension sine theta 1. All right, and then I'm going to look at the same picture again. I'm going to look at it again and I'm going to say, what is the summation of the forces in the y direction? Okay, well that's going to be the force of tension, the cosine of theta 1, minus m1g, and that has to also equal 0 because the forces aren't moving. All right, so the force of tension 1 is going to be m1g divided by cosine theta 1, and the force due to electromagnetic stuff is going to be m1g divided by cosine theta 1. And from that we're going to get that m1g tangent theta 1 is equal to m1g theta 1 when theta 1 is small. And theta 1 is small. Right. Okay. So that seems to be okay. Now we're going to do the same thing on the other side. And say, we're going to look at the other side of Q2, and we're going to see that the force due to the charges at 2 is going to be m2g theta 2. And since the force due to the charges at 1 has to equal the force at the charges over 2, which means that m1g theta 1 has to equal m2g force of gravity theta 2. That implies that theta 1 over theta 2 is going to equal m2 over m1, which is going to be equal to 1. Okay. Now, I'm going to do part 2. I'm going to do it over again. And so part B, so that's the answer to part A. So in part B, we're going to have Q1 equal to Q, Q2 equal to 2Q, same as before, but now we're going to have M1 equal to M and M2 equal to 2M. Okay, so we're going to use the same reasoning and say that in that particular case, then the M1G theta 1 has to still equal M2G theta 2. We don't have a choice there, so theta 1 over theta 2 has to be M2 over M1, which has to be 2M over M, which means my ratio needs to be 2. Now we're going to do part C. Estimate the distance between the two spheres in each case. Alright, so I look at that again, and I have these guys like that. And so case 1, the A case, theta 1 is equal to theta 2. And so I got some length there. I got some length over here. I got length over there. And now the issue is, what is the length there? So the sine of theta 1, sine of theta 1, we'll call it D, is equal to D over L. Okay, so the distance D is going to be L, say theta, sine theta 1. And so 2D, which would be the total length between them, would be 2L sine theta 1. And then you could say, because theta is small, we could say that that's going to be 2L theta 1. We could drop the sine portion. Alright, so now I know that D, 2D, we'll call it capital D. The distance between the balls is going to be 2L theta 1, which means theta 1 is going to be D over 2L. And then we're going to put that back into our equation, and we say, well, M1G theta 1 is going to be the force caused by the charges 1 over 4 pi epsilon naught Q1 Q2 divided by D squared. Okay. And in case 1, Q1 was equal to 2Q2, okay. Okay, and that this has to be mg, distance between them, over 2L. And that little d there should be a big D. It's a little d in our equation, but we're using a big D now because of my inconvenience use of variables. All right, so we're gonna rearrange this equation and say d cubed is equal to 1 over 4, we'll make that a k. Make that a k, q, 2q, 2l divided by mg. G. And we'll say the distance between these guys for case 1, the A problem, is going to be 4K Q squared over mg, and then we'll take the cube root of it. Okay, so that's the first guy. Case 2, we have that that theta 2 over theta 1 has a 2 this time. So we'll go with something different. We'll say that the distance, and we'll use a capital D again. The distance between the two is going to be L theta 1 plus theta 2, because the sign of theta is very close to theta, because theta is small. Okay, and so that's going to be 3/2 L theta 1. Alright, so theta 1 is going to be 2D over 3L. Now we're going to plug that guy back into our equation and say that K Q1 Q2 over D squared is equal to mg 2D over 3L. And then we're going to rearrange things again and say D is equal to 3LK Q squared over mg raised to the 1/3 power. And I hope I didn't skip too many steps there. Oh yes, I do. I hope I skipped more than enough steps. Right, exactly. Okay, I'm going to do number 28 next. Determine the magnitude and direction of an electric field at a point midway between a charge of minus 8 microcoulombs and plus 5.8 microcoulombs. And the charge are 8 centimeters apart. Okay, so we have 4 centimeters on this side, 4 centimeters on this side, and we know the author is trying to hose us over because we have to keep those distances in meters in order for them to work in the equations that we have. And though the charges are nearby, we want to determine the direction and the magnitude of the field. So we'll come up with the magnitude of the electric field first. So my electric field is is KQ over R squared. KQ over R squared. Right. And the magnitude is going to be the guy from the first guy plus the guy from the second guy. And so that's what we're looking at. So I'm going to have K times Q 8 microcoulombs divided by 0.04 squared plus 5.8 microcoulombs divided by 0.04 squared. And I didn't get that bracket right. And I'm going to end up with 7.8 times 10 to the 7th newtons per coulomb. Now, the issue is which direction is it going? So direction, and the direction of an electric field is always going to be from the positive guy to the negative guy. So the electric field is going to be going from positive to negative. So if I would have driven this picture the other way and put the 5.8 microcoulombs on this side and the minus 0.8 on that side, I would still go from the positive to the minus. So the direction is from the positive charge towards the negative charge. And just a coincidence of the drawing that happens to be in the minus I direction. Okay, now we're going to move up and do problem number 50. We have a thin glass rod that's in a semicircle of radius r, and it has a uniform distribution along the rod, and the charge density is given lambda is equal to lambda naught sine theta, where lambda naught is a positive constant. We have some point P at the center of the semicircle. Alright, so what we need is a better than normal drawing. Okay, so there's the x direction, there's the y direction, and I've got a semicircle going like that, and we have some distance r like that, r, and some theta, and it looks like we have positive charges on the top half of the semicircle and negative charges on the bottom half of the semicircle. And we're going to ignore the fact that there's some thickness there, probably. We might do that. Okay, hint. Remember that sine minus theta is sine theta. So the two halves of the rods are positively charged. Okay, so we don't have a positive charge on one side and a negative charge on the other side. We have positive charge on both sides because lambda is equal to lambda naught sine theta. So in order for that to be the case, when I go negative down here, I'm not going negative, it's really positive. Okay, so that's interesting. Thank you very much, author, for telling us that. Alright, so what are we supposed to be calculating anyway? Find the electric field at P. Alright, so from a spot up here, I'm going to be going towards P. And all those spots are going to be going towards P. And these are going to be going towards P as well. So what that means is that my field is going to be symmetric, which means that in the y direction I have no field, because whatever I have in the y direction from one guy is going to be canceled out from the guy on below, and the only field I'm going to have is going to be in the x direction. Okay. I look at this and I find that lambda is lambda naught theta whatever, but that the change in Q is going to be lambda r change in theta. So as I look at this, lambda is my charge density, and my change in that in Q is going to be as I change theta, my lambda times my r. Okay, so that looks reasonable. So my change in my electric field, 1 over 4 pi epsilon naught, doesn't look too much like an epsilon naught. We'll try again. Epsilon naught lambda r d theta r squared. All right. D we're symmetric to the x-axis. Okay, we're reconsidering our original picture. The author was not trying to tell us that these are positive charges. These are in fact negative charges. Because these are in fact negative charges, the horizontal horizontal components of these charges are canceling out. Because I'm going positive to negative, positive to negative, we're only going to have a vertical component to what we're doing. So this equation is for the vertical component, and we're going to substitute back in for y, for lambda, that lambda is lambda naught sine theta, and we're going to get 1 over 4 pi epsilon naught divided by r sine squared theta d theta. And then we're going to go and integrate that from so the vertical field going to integrate from minus pi over 2 to pi over 2, so that'd be minus 90 to plus 90. Lambda naught, where did lambda naught go? Lambda naught, that's where it went. Lambda naught 4 pi epsilon naught r sine squared theta d theta. And so we're going to get, bringing out the constants, lambda naught 4 pi epsilon naught r, and we're going to have 1/2 theta minus 1/4 sine theta 2 theta, evaluated by between minus pi over 2 and pi over 2. And I'm pretty sure you have a integration table that's going to tell you how to do that. Alright, And so we're going to get lambda naught over 4 pi epsilon naught r. And this is going to end up with 1/2 pi. Because in both cases, sine of pi is 0, sine of minus pi is 0. And the only thing we have left over is 1/2 pi. Because we have 1/2 pi minus 1/2 pi over 2, pi over 2, pi over 4. Okay, so that's fine. Which is lambda naught over 4 epsilon naught r. And then we ask ourselves, well, what direction is the field going? Well, it's going from the positive to the negative. So, and the electric field needs to have a vector direction quantity. So I'm going to have minus lambda naught over 4 pi 4 epsilon naught r j hat. And that's going to get us in the right direction. All right, now we're going to look at the B part of the problem. 50B. Determine the acceleration of an electron placed at point P, knowing that the radius is equal to 1 centimeter, 0.01 meter, and that lambda naught is equal to 1.0 microcoulombs per meter. Okay, force is going to be mass times acceleration, is also going to be Q times the electric field. So we got Q times the electric field, lambda naught divided by, better put a minus sign there, 8 epsilon naught r j hat. Alright, so my force is going to equal 1.6 times 10 to the minus 19th coulombs, the charge on the electron, times 1.0 times 10 to the minus 6 coulombs per meter, my lambda naught, divided by 8. Mass of the, we're trying to find the acceleration. We're going to have to move back. Alright, so I'm going to find the mass of the acceleration. So the acceleration of the electron minus Q lambda naught 8m epsilon naught r j hat. Okay, that's better. So the charge on the electron, 1.6 times 10 to the minus 19 coulombs, 1.0 times 10 to the minus 6 coulombs per meter, my lambda naught. My 8 stays in 8, mass an electron, 9.11 times 10 to the minus 31 kilograms. Epsilon naught, 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared, times my R, 0.01 meters, and I almost ran out of space. I put that in my calculator, I get 2.5 times 10 to the 17th meters per second squared in the j hat direction. Okay, and the electron, if I put an electron there, it's going to go towards the, it's going to go up. It's going to go towards the positive charges, and that's why this is going to be in the positive j hat direction. Alright, well, so much for problem number 50. Now we're going to problem number 56. An electron with a speed 56. Okay, so I've got some electron traveling at 27.5 10 to the 6 meters per second. It's traveling parallel to a uniform electric field. Okay, so this is an electron. I got some uniform electric field, and 11.4 times 10 to the third newtons per Coulomb. Okay, that's fine. And my electron is traveling parallel to that field. So it'll be going the other way. Gosh, it'll be headed towards the positive charges. Alright, well, that's how far will the electron travel before it stops? Alright, so it's traveling that way so it can stop. Okay, before it starts going the other way. Alright, so that makes sense to me. Okay, so that being the case, the force on the electron is mass times acceleration, which is QE, which is minus E times the electric field. Okay, from that we can get that the acceleration minus E, capital E over M, what we want to find is how far the electron's going to travel before it comes to an end. Okay, so we go back to our physics 1 and we find that the velocity squared when I get done is going to be velocity naught squared plus 2m delta x, and that's going to be 0 because I am stopped. Alright, so that it's going to be the case. So how far do I go before I stop minus velocity naught squared divided by (2m). 2a, acceleration. That's an A. Everybody was telling me that that was an A too, and no one was paying attention. A. Alright, is that better? Minus velocity naught squared over 2, and I know my acceleration is minus E, capital E, divided by mass. So I end up, my distance is going to be m velocity naught squared divided by 2e capital E. And so I put all those things in my calculator. Mass of the electron, 1.99, 10 to the minus 31 kilograms. My velocity, 27.5, 10 to the 6 meters per second. The quantity squared divided by 2 times the charge on the electron times the electric field times 10 to the, what's the electric field anyway? 10 to the third newtons per Coulomb. And I put those numbers in my calculator and I end up with 0.189 meters is as far as he's going to go. And then I ask myself, so how many significant digits do you think we have? 333, we have 3 significant digits, so I would stay with that particular answer. Then we want to find the time, how much time will elapse before it returns to its starting point. Okay, so we we have some electric field, we have some guy that's going that way, some electron going that way. When it stops, it's obviously going to turn around and come back, and the amount of time it takes to go one way is the amount of time it takes to go the other way. Okay, so we know that velocity at times t is equal to velocity naught plus at. We know that that's the case. And from that we can come up with the time is going to be v minus v naught divided by acceleration. And and we decide, well, that's minus 2 times v naught because the velocity I'm going to is minus v naught. So minus 2 times v naught, because I'm going the other way, divided by E, big E, divided by mass. So I end up with 2 mass velocity naught over E, little e, and that's going to be the time it's going to take for this guy to get back to where it started from. Alright, so I'm going to have 2 times the mass times the initial velocity divided by the electron, coulombs in one lousy electron, 19 coulombs, times the electric field. And I throw all those numbers in my calculator and I find that the electron will get back to where it was coming from in 2.75 times 10 to the minus 8 seconds. And again, I have 3 significant digits, 3 significant digits in my answer, so I am happy about that. Okay, we're doing number 64 next. Suppose both charges in figure 2145. Now I got to go find figure 2145. 2145. Okay, I'm looking at 2145 and I see that I've got some point P and I've got some Q and I got another Q over there and I've got some distance R going down that way to a right angle, and I have that's a right angle, and I have L over 2 on this side and L over 2 on that side. Okay, so I got the right picture. We're positive. Okay, so both charges are positive. Show that the field on the perpendicular bisector for R, which is much greater than L, is given by something. Okay. Alright, so R is much bigger than L. Alright, so that's alright. So I've got some angle on this side. We'll call that theta 1. And we'll call this guy theta 2. Alright. Now, we find that the electric field, both of these guys are positive, is going to be in the y direction only, because I got a field 1 going that way, a field 2 going that way, field 1 going that way, and the resultant of those fields is only going to be in the y direction. Alright, so I know that. So the issue is, what is the net field okay, so the net field 2E, because there's two of them, sine of theta. Okay, so E sine theta would be the field at any particular point, and because there's two of them, would be 2E sine theta. Okay, so that's going to be 2Q over 4 pi epsilon naught r squared plus L squared times R divided by r squared plus L squared to the 1/2. And maybe you see that, maybe you don't see that. We hope you do. And that'd be 2 over QR divided by 4 pi epsilon naught r squared plus L squared to the 3/2, because L is so much smaller, L is so much smaller than R. We can rewrite that and say that this is going to be 2QR divided by 4 pi epsilon naught R cubed. And that doesn't look like an epsilon naught to me. Epsilon naught. And so we'd say the net field is approximately that. And because this looks sort of like a subscript, we're going to make it a little bit bigger. R. There, is that better? All right, now the B part of the problem. Explain why the field decreases as 1 over R squared, whereas for the dipole it decreases 1 over R cubed. Okay. So B, explain this. Since both charges are the same, both charges are the same, and L is much less than R, when I'm going up the horizontal, it appears to me that I only have one charge of 2Q, in which case E would be KQ over R squared, which would be 2Q 4 pi epsilon naught R squared. And now I'm related to R squared instead of R cubed. Okay, number 66. Suppose the dipole P is placed in a uniform electric field E So my electric field is going to be E I hat, okay, that points along the x-axis. If E depends only on x, show that the net force on the dipole is something. Okay, so that is what we're going to do. Okay. So we're going to use equation 21-10 and say U of x is equal to minus P, the dipole moment, and times the electric field. Now, since the potential energy is known, we're going to use equation 8-7 and find that the force in the x direction is minus du dx, and that minus du dx times minus P, dipole moment, the electric field. So we have that, and since the dipole moment is not dependent upon x, this is equal to the dipole moment dx E, the derivative of the field. Is that what we're supposed to do? We're supposed to, and because this is a x, it's going to be in the x direction, so we can throw on an I hat. Right. Alright, I guess we're done with that. That makes us done with chapter 21. Now, what you've seen is pages and pages of work done on problems, and that is what I expect you to do as well on your homework, is produce those pages of work and send them to me. Okay, thank you very much.